Hi everyone, good morning all. Welcome back to our EV channel. Today we are going to discuss about what is the need of DC motor drives in electric vehicle applications. Before going to this, now let's try to recall how this DC motor works, what are its components and how to apply Fleming's left hand rule to find the direction of a force experienced by an DC motor. So basically the need of an DC motor and electric vehicle drive is when you require an adjustable speed. So if you require an adjustable speed, if you want an adjustable speed, then DC motor is required. And to have good speed regulation, okay. So if you want an good speed regulation, then a DC motor is also a perfect tool to you. So okay, what is this speed regulation is? Speed regulation is also called as speed drop. Okay, so the drop in speed should be minimum or maximum. So this should be minimum. Okay, if it is minimum, I can say our DC motor is having good speed regulation. So what is speed regulation means? The drop in speed should be minimum. For the increase of load, how much is the speed decreased on the motor is called as the drop in speed should be minimum. So this speed regulation I'm going to define it as so no load speed minus full load speed divided by full load speed. Okay, so when you write down this regulation, so here this no load speed generally I'm taking it as a 1500 rpm. Full load, after loading it is running with a 1400 rpm divided by full load. So when you perform this, you are going to get as 100 divided by 1400. So you can see here with respect to 1500, 1400 is lower. If you get it as lower, you are going to get the speed regulation up. So we are going to calculate here the up speed regulation. Okay, so we are going to calculate up speed regulation. I mean, what is the maximum possible of speed regulation is possible by this speed regulation or the DC motor we are going to calculate. So this speed regulation should be good. If it is a offering good speed regulation means the drop in speed is minimum. The drop from no load to full load is minimum. So for example, if the drop is here it is having 1480, then what is the drop? It is only 20. Okay, the drop in speed should be minimum. For the increment of mechanical load, for the increment of full load, the vehicle has to supply the required amount of power or the torque or the speed in such a way that the speed difference will be minimum. If the speed difference is minimum, I can say that our DC motor is having a good speed regulation. This is all about our DC motors. Our DC motors already by using two methods, we have adjustable speeds and they have good speed regulation. That's what the meaning of good speed regulation. The change in speed from no load to full load should be minimum. If it is maximum, it's a bad speed regulation. It is unable to withstand the load. So third feature what we have in our DC motor is, so we can frequently start a DC motor, we can frequently stop a DC motor, and frequently by changing the field winding or armature winding, we can reverse the direction of an DC motor. So frequent start, stop and reverse is possible with the help of DC motor drives. That's why the DC motor drives are used in EV applications. So various DC motor drives have been widely used for traction purpose. In all the traction electric vehicle traction purpose, DC motor is used. It has a wide speed range. So this DC motor is used in traction, is used in electric vehicle because of their technological maturity as well as a speed control. Now let's try to come to the operating principle of an DC motor. Okay, it's very simple to understand. No need to bother more. So coming to the working principle of a DC motor. So coming to this working principle of an DC motor, what happens is, so when you take an DC motor, you are going to have two parts. So you are going to have two parts. One is stator and another one is a rotor. Okay, so this rotor is made up of a winding where this winding is called armature winding. So what is meant by armature means armature is nothing but some set of conductors. This set of conductors are called as coil. So set of conductors is called coil, and set of coil is called as winding. So like this, more numbers of windings are there. These windings are called as a armature. Okay, so in the rotor part, we are going to have some conductors and indirectly some set of coil, and group of coils is called winding. So this is called what you have in the rotor. But in the stator part, you are going to have the field winding. So here we are going to have the field winding. The purpose of this field winding is to produce the magnetic flux. The purpose of this armature is also to produce magnetic flux. Interaction of this will try to propel our DC motor. So now coming to here, the parts. So now here you can see here. So here you have the rotor and here you have the stator. So this is nothing but the rotor of our DC motor, which is made up of which winding? Armature winding. And coming to the stator, so this is nothing but the stator of our DC motor, which is made up of a field winding. So this field winding has some, this is nothing but iron core. On this iron core we are having some winding. This winding will make this as an electromagnet. So now you see here the flux travels from north pole to south pole. So the flux is traveling like this from north pole to south pole. So now what is the force experienced by the conductor? Now the formula, the force experienced by the conductor, F is equal to B I L sine 90. So this 90 is the angle between flux and the current. Okay, so the angle between the flux and current is 90 degrees. Now how it is 90 degrees, you can see here. So the force experienced by the conductor is directly proportional to magnetic flux density. Okay, so this is nothing but B is called the magnetic flux density, where flux density is equal to flux per unit area, and I is the current carried by the armature, and L is called as the length of the conductor in armature. Okay, the angle between this flux and current will is 90 degrees. Therefore BIL is the force experienced by the conductor in the magnetic field. This is the amount of force experienced by the conductor in magnetic field. Now let us try to see this, how it happens. So already I told, so the magnetic force, this is nothing but the field winding. The flux travels from north pole to south pole, it is traveling, and you are having the armature, which is like a cylindrical in nature. You have the number of windings. So here what happens is how the force is experienced. Let's try to apply here. So whenever the magnetic field is flowing, and you can see this in detail, the structure also. Here you have the stator, and this stator is made up of some iron core, where this is called pole shoes or pole faces. On the stator, what kind of winding you are going to have? Field winding. So this is nothing but completely the field winding to produce the magnetic flux phi. And inside this is called as stator. Inside this, which rotates, is called as rotor. This rotor is made up of a winding. This winding is called armature winding. So these windings are brought out, and they are bought out with the help of an commutator. So I want to collect this. If it's a case of a generator, I want to collect this, or I want to give the EMF, I can do it with the help of an commutator and brushes. So if you want to give the supply, you have to give the supply to positive here and negative here. The armature gets excited, and this will be available in the higher inside the rotor and starts propelling in its direction. Now we are discussing about the motor. We'll discuss more about that. And the way you supply the supply to the armature is, you will give the supply here and it goes into the brushes. Through brushes it goes to the commutator. Through commutator it is available across which winding? The armature winding. This complete armature. So here the armature winding is there. This is how completely it is available across the armature winding. This is the parts, this we are going to call it as armature, is already I told. So now we want to identify the direction of a force experienced by the conductor. In order to identify the force experienced by the conductor, we are going to have an Fleming's left hand rule. So Fleming's left hand is like very simple to understand. We have two types of rule, Fleming's right hand rule. So here how many R's are there? 2 R's are there. In a generator also, just I am giving a clarity, the generator, one R is there, one more R is there. How many R's are there? 2 R's is there. So Fleming's right hand rule is applied for the case of an generator. When coming to the Fleming's left hand rule, motor, okay, MOTOR, how many R's are there? 1 R is there. Therefore we are going to apply, it's not like that, just an logic how to overcome the confusion. So here in motor 1 R is there, here also 1 R is there. This is nothing but for the motor we are going to apply Fleming's left hand rule. So coming to here, you take your fingers. You can see here the flux lines are traveling. Okay, so this is the, you can see here the forefinger indicates the magnetic flux, which is nothing but A. So the center fingers indicates the direction of current, which is nothing but how it experiences the current. And coming to the thumb, it indicates the force. So here there are two types of current polarities. One is cross, which is away from the observer. When the current is flowing away from the observer, then we are going to call this as a cross. When it is dot, it is coming towards the observer. The current is flowing towards the observer. So in this case, you can see here your magnetic lines of force are traveling in this direction. Okay, and you can see here you can rotate this, the current here it is towards the observer. So this is nothing but you have to reverse it like this. So this is the magnetic lines of force are going in this direction and the current is towards the observer. These are coming to us, and you can see here force experienced, okay, is downward direction. Okay, so that's how it is having a downward direction. So when you take this rotation and you have to rotate it, it is towards this direction, and here the current is, here the current is towards the observer and the direction of force is downward. Or if you want to take here, here you can understand better. So the magnetic lines of force is traveling from north pole to south pole like this. It is traveling like this, and current is towards the observer. So this is the direction of current, which is towards the observer. The magnetic lines of force are traveling from north pole to south pole. This is B. And when you see the force, you can see here the current flows, I mean the force experienced is also to the downward direction. Okay, so the force experienced is nothing but the downward direction. Okay, so you can see here the force is experienced in this will be like this, and the force experienced is downward direction. If you take your hand, then you can only understand better. So just take your left hand and keep the take your left hand and keep the flux direction like this in such a way that so here you are having the forefinger, okay, and at the bottom is nothing but your thumb. If you project your hand, then you can understand. So this is nothing but your forefinger, this is the thumb, and you can hear the center. The center is towards you, where this is nothing but a dot. Okay, so here current is towards the observer, but when you come here it is reverse. Okay, so here these are nothing but the force experienced is downward direction. Here the force experienced, here you can have here the magnetic lines of force are traveling from north pole to south pole. Take your left hand and creep in 390 degrees as shown in this figure. So north pole to south pole, it is traveling like this, and here the current is towards the observer. Okay, so here the magnetic lines of force are traveling from north pole to south pole, and current is away from the observer. So here the current is going away from the observer. Here it is maintaining 90 degrees, and here you can see here the force experienced is in forward direction, I mean the upward direction. So this is trying to move in this direction, and this is trying to move in this direction. Automatically a twisting force is produced, where this is called torque. Very simple to understand. This you can understand only when you physically see it here. So in this, if you take, so in this direction thumb is there, and here the force will come to downward direction, and the center finger will be facing you. Okay, so this is how we are going to find the direction of force experienced by the conductor inside the rotor. When you have here, there is nothing but dot indicates the current is towards the observer, cross indicates it is going away from the observer. So you have to take your hands like this, you have to project your hands like this, and you apply it how I told. So your forefinger is dash direction, and the current is projecting you, and automatically the thumb will be in downward direction. Okay, this is how to understand the force experienced by the conductor due to these two forces acting in opposite direction. This force is moving in one direction, this direction moving in opposite direction. Resultantly it will develop the torque. That's how a torque is developed in an DC motor. Okay, so that is all about the development of torque in an DC motor. So I think you are able to understand what is meant by stator. I'll review it. So you have two types of windings. So one is a stator and another one is rotor. In the stator, you are going to have the field winding. With the help of pole shoes, we inserted the field winding, which is used to produce the flux. And in the rotor, you are going to have the armature. In this armature, you are going to have set of windings. The purpose of this armature core is to insert the winding, and you can make this DC motor to run when you supply the supply. So through positive it goes to the brush, through brush it goes to the commutator, through commutator it goes to the armature winding. That's how the interaction between the flux produced in the field and the flux produced in the armature. Due to this interaction, a force is developed like this. This force will try to pull you downward direction, this force will pull you in upward direction. By applying Fleming's left hand rule, that's how a torque is developed in an DC motor. So this is all about the basics of an DC motor. Now let's try to derive the expressions for the torque induced in an DC motor. Okay. So now coming to here, the expression, I mean the EMF induced or the back EMF induced in an DC motor is given by the formula flux into number of conductors into speed multiplied with the poles divided by 60A. So I want to write down in an simplified format. So I'm going to multiply this equation as 5Z NP divided by 60A. I'm going to multiply into 2 pi, and I'm going to divide into 2 pi. So when I'm going to multiply here, I'm going to segregate this as omega. So I want this term as separately, and 2 pi n. So this is 2 pi n, and this 60 as separately. So these three terms I want separately. Okay, so therefore I'm going to find it as 5 into, so 2 pi n divided by 60, we can write it as a omega, where omega m is called as a angular velocity of the armature. So where omega is called angular velocity of the armature in radian per second. Okay, and what is the left terms now? So 5 completed, 2 pi n divided by 60 completed. So the left terms are Zp divided by 2 pi a. So this Zp divided by 2 pi a, where I am going to call it as a K E, and this is a product of flux into angular velocity Km. So this is how the EMF induced in a generator, or the back EMF, this is called EMF in the case of a generator, back EMF in the case of an motor. So this is how the EMF is induced in an generator. And now let's try to discuss about the torque production. Okay, so the torque production is, so we have the formula for, in order to derive the torque, we are going to equalize the electrical power with respect to the mechanical power. So electrical power, you can write down it as E into IA, where mechanical power you can write down it as power into angular velocity omega. Okay, now let's try to do this derivation. So EMF induced can be, or back EMF you can write down it as phi z n phi z np by 60A multiplied with IA. And how to write down the power? So directly we are writing this mechanical power as torque into omega, so torque into omega you can write down it as 2 pi n divided by 60. So here n by 60 will get cancelled out, here n by 60 also will get cancelled out. So now here I am separating, I want flux as separate and IA as separate. Therefore torque is equal to flux into IA. What are the left terms now? Pz, okay, Pz divided by A, and this is in numerator, denominator it will come to the denominator. So you can see here Pz by 2 pi A, we are going to call it as the torque. Okay, so the torque produced by an electric vehicle is nothing but a DC motor. Ke is equal to flux into Ia. This is how the torque is experienced by an DC motor. So this I can write down it as torque is proportional to flux into armature current. Okay, so this flux is produced by which winding? Field winding. So this flux is produced by the field winding, where this field winding is present in the rotor. This current is produced, armature current is produced by which winding? Armature winding. And where this armature winding is there, this armature winding is there in rotor, and here the field winding is there in stator. Okay, so now the availability of armature current and availability of field flux is directly proportional to the flux. If you are able to have permanent magnet and required amount of flux, the torque is also maximum. If you are able to supply required amount of current to armature, the torque is also maximum. That's how the torque is produced in an, or the relationship between the field winding flux and armature current in an DC motor. So very simple to understand. Here this flux is called field winding. This flux is produced by the field winding. The field winding is present in where? Stator. And this armature current is produced by the armature winding, and this armature winding is there in the rotor. Already I discussed here, you can understand here. So this armature winding is available at rotor, and the field winding is available at stator. So the product of armature current and field flux is nothing but the torque produced. This is all about the derivation of torque in a DC motor. Now we'll try to continue with different types of motors, how we have self-excited and separately excited. We'll meet in the next video. If you feel the content is useful, please give one valuable like, please share with your friends, and if you feel the content is very useful, please subscribe our channel, and please forward these sort of channels to your friends, those are studying electric vehicle subject. And this is like a free channel. This is only for the betterment of students, which will help them to study well and to get jobs in electric vehicle domain. Thank you for watching. Yours obediently,